All right, we're going to keep going with our work on counting in the world of probability, and today we're going to look at combinations, and we'll do an introduction and some examples. So the word combination in probability has a very specific meaning. In general life, combinations mean something a little bit more general, but very specifically in combinations in probability, combinations means the number of ways that we could group some different things together. Okay, so you're going to use combinations when all objects are different and you don't care about the order of the objects. Okay, so it's not like when you're lining things up against the wall or you're arranging paintings on the wall or something. You're finding groups here where the order doesn't matter. Okay, so if you have a group of Alice, Bill, and Charlie, that's the same as having a group of Bill, Charlie, and Alice. So that would count as just one combination. And just like with permutations, you're not necessarily using all the objects. Okay, so there's a particular formula. I'm going to lay it out here, and then also I'm going to try to explain why it works a little bit. Okay, so this might look familiar to you. This part of my formula is the permutations formula. So we're sort of taking the permutations outcome and then dividing it additionally by an r factorial. Okay, so we'll do a quick example in a second, but let me explain some terminology here. So this could be read as NCR. It could be read as N choose R. But in the world of combinations, you're really looking for groups, committees is another kind of a key word here. Groups or committees or choose. So I'm going to try to be really careful in this class, in these videos, that if I ever say the word choose, I'm going to be referring to combinations. If I say the word pick, I'll be referring to permutations. And if I don't want you to clue in on which one we're talking about, I'll usually say the word select, okay, if I don't want to give it away. All right, so let's say we had 10 people as a quick example. I want to try to explain this formula. And let's say we want to arrange 3 of them in a row, okay? We would do our permutations formula, which is 10 factorial divided by 10 minus 3 factorial. Okay, and we would get a particular number for that. However, for each of those 3 in a row, maybe they're Alice, Bill, and Charlie, right? A, B, and C. Let's say maybe after a little while we decided we didn't care about the order, we just care about the groups that we're creating. So in other words, how many ways are there of rearranging A, B, and C? Okay, I'm trying to use some arrows here to show that we're mixing A, B, and C up. Well, you can think about slots. How many ways could we arrange those people? 3 times 2 times 1 is 6. That's 3 factorial, right? So the permutations, this calculation here counts all of those 3 factorial ways for each group of 3 as separate ways. So if we decide that eventually we want to just start dealing with groups and we don't care what the order is, we would modify the permutations formula. So this is 10 pick 3. We would modify it to be 10 choose 3. We would write out the same permutations formula, but then we would also divide it by that 3 factorial, okay? Just so that we're not double counting all the different arrangements that the same group of 3 could be. So that's where that r factorial came from in the formula right here. Okay, so hopefully that explains it a little bit. Your calculator should have a button for combinations. It should be probably right next to the button for permutations. Let's do some examples. So the local ice cream shop has 25 flavors available. I want a bowl of 3 scoops. How many options do I have? This is the one we're going to do both ways, okay? And then we're going to do it by hand, sort of, and then we're going to use the NCR button on our calculator. But for all the rest of them, we'll just be a little more efficient and use the calculator. So we want to do 25, choose 3. We're looking for groups of 3. The order doesn't matter. Okay, so when you're getting a bowl of ice cream, does it matter if the vanilla's on the left, the chocolate's on the right, and the mint chocolate chip is in the front? You know, it doesn't matter. Okay, so we're looking at groups. So let's do our permutations formula, and then let's also divide by the 3 factorial. Okay, so the 25 factorial is going to be mostly canceled out by the 22 factorial, and then we're going to divide this guy by 6. We can actually do a little bit of canceling here. And 25 times 4 is 100, so we should have 2,300 different ways of doing this. So let's test it on our calculator as well, and I'm going to do 25, choose 3. 25, choose 3. And I also get 2,300. Okay, so that checks out. The math checks out. All right, next one. And this is based on a totally true story, maybe a little bit goofy, but true story. Whenever my dad and I are at a fancy dinner and someone makes a toast, we both try to be the first to calculate in our heads how many clinks of glasses there are. Okay, so if everyone clinks their glass with every other person, how many clinks would there be? And it's sort of this weird mathy tradition we have. But I want you to realize that this is the same problem as asking how many handshakes there would be in a group if everyone shakes hands with everyone else. Okay, so in our class of 25, how many handshakes would there be? And what you need to think about is that if I shake hands with Lily, Lily then doesn't also have to shake hands with me. Okay, so in other words, order doesn't matter. We're just looking for groups of 2. How many different unordered groups of 2 could we make to create some handshakes? So this is going to be 25, choose 2. Okay, that's 25 times 24, but then we need to divide by 2, so that order doesn't matter. But your calculator should have a choose button, and that's going to be 300. So 300 different handshakes in our class of 25. Next one, we're making groups of 5. So same class of 25 people. I am making groups of 5 for a project. How many possible groups would include both Hope and Spencer? So this is like one if you watch the video with the stuffed pug and wombat animals. It's very similar. Let's pretend Hope and Spencer are already in the group. Okay, and they're already kind of merged together. We don't have to think of it as carefully as the pug and wombat example as being sort of merged together to take up one slot. But let's pretend they're already in the group. So how many different groups could we make up that include Hope and Spencer in them? So Hope and Spencer are kind of out of the running. So we have 23 people. And how many people are we choosing? We're choosing 3. Okay, so this 25 turned into a 23 because Hope and Spencer are already in the group. And this 5 turned into 3 because we only need to choose 3 more people. Okay, so go to our calculator. 23, choose 3. 1771. Okay, so that's how many different groups would include both Hope and Spencer. So last example here is class of 25 people making 5-person groups. What's the probability that Hope and Spencer are in the same group? So probability, remember, is the number of ways of getting Hope and Spencer together divided by the total possible groups. Okay, so we already figured out how many ways Hope and Spencer could be together. That's up here. That's 1711. Okay. And how many total possible groups are there? That's 25, choose 5. Okay, and some of those groups have Hope, some have Spencer, some have both, some have neither. Okay, so 25, choose 5 is 53, 130 as our denominator, 1711 up top. And we get a 0.0322 or about 3.22%. So that's the chance that Hope and Spencer end up in the same group. All right, and that's a good place to stop.